Okay, welcome back. We're reconfigured now, and we've got the 7-member crew for the STS-61 flight joining us now. I will introduce the commander, and then he in turn will take care of the rest of the crew for us. So with that, I'll turn it over to Commander of the flight, Richard Covey.
Thank you, Kyle. Well, it's really great to be here today. This is another milestone in preparing for flight. Milestones have been flying by for us recently. I'd like to quickly introduce the rest of the crew and tell you what their positions are on the crew. On my right is Ken Bowersox, is our pilot. He backs me up on all flying duties and also is an RMS operator. Backs Claude Nicollier up on that. On his right is Claude Nicollier. Claude's a Union Space Agency astronaut, and Claude is our primary RMS operator. Additionally, he's flight engineer and has done all of the ascent and entry training and rendezvous training with Sox and myself. On the right is Story Musgrave. Story is the payload commander for this mission. He's been assigned to the crew the longest, well over a year and a half now, and Story, as a payload commander, is also one of our EVA crew members. When he's not EVA, he will be intravehicular activity or IVA crew member, and will be directing the activities of the other EVA crew members. On his right is Tom Akers, and Tom, in addition to being an EVA crew member, will be playing the same role as the IV crew member, intravehicular activity member, when Story is out on his spacewalks. And to Tom's right is Jeff Hoffman. Jeff is another EVA crew member. Of course, we have 4 of them, and in his role, he also will be one of our primary payload operator, and will operate the interface the crew has with the payloads and the payload support systems. And on his right is Kathy Thornton. Kathy's at the end, but she's another important member of our EVA crew, and also when Jeff is outside will be performing the payload interface function on board the orbiter. We are a privileged crew to be able to fly on this mission. There are plenty of astronauts in our office that can go and do the jobs that we've been asked to, and we know that. We therefore feel very lucky to have been asked to do this mission. At the same time, we also think that we're very good and that we will be able to perform exceptionally well in the course of the events that are planned. We have had some of the most intensive and extensive training that I have ever experienced in preparation for a space flight. That started with members being named early. It continued with the use of resources and facilities that had been used before in the development of plan and in the training of crew members. And it continued in the number of hours that we have used certain resources, particularly neutral buoyancy. Far many more hours for this flight than have ever been used before for a space mission, space shuttle flight, and an extensive number of hours in payload-related activities, working with the Hubble payload itself, and not in a neutral buoyancy environment, but in a room environment, fitting tools and preparing for the activities that the EVA crew members will have to achieve in EVAs. We have been fortunate in that we have received incredible support in our preparation for the mission. We haven't had to ask for priority in anything. It's just been given to us because of the importance that people have put on the accomplishment of the Hubble servicing and repair. With that, I'll turn the mic over to Sox to talk a little bit about the first activities of the mission. I know you've been briefed on the overall mission overviews recently. The fact that it's 11 days, and the first thing we have to do after we get into orbit and get things squared away is to proceed on to the Hubble Space Telescope. Sox.
Well, the rendezvous with the telescope actually starts right at liftoff. The orbiter's computers will be using the main engines to get into a precise orbit, so that 2 days later we'll be able to catch up with the telescope. Large series burns, ohms, and RCS burns that we'll be doing so that our orbits match up nicely. As the rendezvous goes on, those burns get closer and closer together. During the burns, they'll be monitoring the orbiter systems along with Claude and I. We'll be working with the ground to make sure the orbiters go just to the right place in the sky. As the pace of those burns increase, I think our excitement level is going to be increased too. The closer we get to the telescope, it's going to be getting bigger and bigger out the window. About minutes prior to rendezvous, Covey will move to the aft station where he'll take over manually, firing the orbiter's RS jets with what we call the TC, the Translational Hand Controller. The primary information he'll be using for that is radar information, which is closing rate and position, and he'll also using his eyeballs, basic pilot skills, to move us in slowly and gently to the telescope. Claude will be in the back, also operating cameras, giving extra information, getting the arm ready for the grapple. I'll be up in front, watching the systems, making the orbiters working like a clock. We expect it will do that. And there will also be some other excitement up on the flight deck. Story, Jeff, and Tom will all have cameras trying to document, kind of like going on in this room right now. Imagine we'll have shit going off everywhere and a lot of cameras in the windows. KT will be using the laser, pointing it at the target, trying to get one X source of range and range rate marks. With all that going on, I hope I'll get a chance to move back and put people away for a few seconds and take a look at the telescope as we're getting in close. Of course, the rendezvous will culminate with Claude taking over with the arm, reaching out, and grabbing the telescope. I'll let him tell you a little bit about that now and the other RMS operation we have on the flight.
Okay, thank you, Chuck. I must say in general that this mission is a dream mission for an RMS or remote manipulator system operator, because there will be more RMS operation on this flight as has ever been in any mission so far. And also more than there will be in the near future, except maybe when we assemble the space station, there will be quite a lot of RMS operation also. Now, the remote manipulator system will not only be used to capture the scope, to grapple it and install it in the back of the cargo bay on the flight support structure, to release it on the 9th station, but also in support of all of the extravehicular activities. All the 5 EVA, which will be talked about a little later by the EVA crew members, will be supported by the arm, in that one of the 2 EVA crew members will be free-floating, and the other one will be on a foot restraint at the tip of the arm, and the RMS operator, Sox or myself, will have to maneuver these crew members from one place to the other in the cargo or toward the telescope in order to do the maintenance job. Now, there's a big advantage in using the arm in support of the EVA operation. On one hand, distances are relatively large between location, the cargo bay, from the protective enclosure where the instrument that has to be replaced are located, and the telescope itself. On the other hand, it facilitates also the handling of large masses, and especially the extraction and insertion of large masses and bulky masses like the high-speed photometer or the corrective space telescope axle replacement, the corrective optics element that will take the place of the high-speed photometer. So the arm will be used extensively in order to facilitate this operation. If we have any failure with the arm, it is anticipated that although we will try to do all this operation, it will quite a bit more time. As I said, on the 9th day of the mission, we will do the release of the telescope. The telescope will be grappled again while it is in that structure in the back cargo bay. The latch will be released. The telescope will be put in position with respect to the orbiter, which is the same as the position it had when we called it on day 3 of the mission, and the release will be performed then. And now I hand over to the EVA crew members to talk about the EVA.
Claude, in fact, very dear to us. It's like a tree picker, and we ride around it. The size of the arm is something like this, and here's the crew person going around. But as he said, in general, we have someone that's ridden on the RMS and another crew person that's going around doing the free floating. At present, we're scheduled for 5 spacewalks to get the total job done. We have another one of 6, which we can dedicate to nominal repair of Hubble. We have a 7th one that we can dedicate to Hubble for any contingency things for deploying of appendages, and we have an 8th EVA in case the orbiter itself has any kind of problems. We're paired up. Jeff and myself will start called the odd couple. I'm not wild about the term. I guess it's true for many reasons. We go out on odd days, 1, 3, 5, and 7, and KT and Tom, they're the even couple. They really are, and they work together, of course, on STS-61 and the Intelsat mission. So we're very, very current on our experience. We all are experienced EVA crew people. The pair, and Jeff and I go to, and KT and Tom, we have that number of days. HST was originally conceived to be friendly to EVA work. It was designed from the bottom up, being able to be worked on by EVA crew people. We are doing some tasks as Katie and Jeff mentioned to you, which were not designed for EVA. That requires some very precision and detailed kind of, but that's the basic plan, is to go out and work pairs every other day until the job's done, to reserve some contingency days. Tom will tell you about all the tools, the kind of hardware that we have to get the job done. We have an incredible flexibility. We do have a plan in terms of pairs, but we can mix up people. We have 4 different sets of suits, and in general, we can interchange suits. We have trained to be able to work with different people. We have also done a lot of training for contingency things, as and Randy mentioned to you earlier. If we get off the flight, which we probably will, we can do any job out there at any time. So Tom will tell you something about the 200-plus kind tools and what the payload bay is like.
Thanks, Story. Of the 10 unique tasks that we'll be required to do on this EVA, Story mentioned most of those were designed quite a while back that we were going to be doing them, and as a result of a lot of people's hard work, we inherited fairly mature procedures and fairly mature common tools to go do the job. We have our tools distributed in various places in the orbiter. Of course, out in the payload bay, which is our area, if you want to think of it as the garage we're going to be working in, we have 3 different toolboxes out there. We have one that is an HST toolbox that is specifically to hold HST tools, and there are approximately 40 unique tools in that toolbox. We also have 2 toolboxes built into the orbiter's payload bay, one of which always flies on shuttle missions and contains approximately 30 unique tools for orbiter contingencies, and there's a spare toolbox that we fill up with unique tools depending on mission, and of course this one contains Hubble tools, again about a dozen unique tools in that toolbox. Of all the tools out in the payload bay, right now all of those are for contingency purposes. If everything goes nominally, we shouldn't even have to get into those unless we want to get some extra tools to help pass down the road. The majority of the tools we're going to be using are stowed inside the middeck and in the airlock. And of those, there's approximately 100 tools that we have inside. Of those, 50 we nominally use. So we know we're going to use those 50 tools. We have another 50 unique ones, and that doesn't count backup, in other words, duplicate tools that we have. In other words, a lot of tools we have 2 and 3 of. In the middeck, we're going to move all those tools out into the airlock. So as mentioned, we're able to go out and do on any EVA day, any task. We have all the tools available in the lock to go retrieve if we need them. Nominally, the 2 people who are out doing a job, one on the end of the arm, he has a platform behind him to stow tools on, and he approximately has 20 tools during any EVA that he can get to immediately. The free floater, on the other hand, the only tools that he can have are ones he can carry. And usually that's just a power tool with some sockets and 2 or 3 tethers. If you think of a garage where you're out working, when you get rid of a tool or you don't want to use it anymore, you lay it down on the counter. Well, we can't do it in the payload bay. We have to keep everything tethered. So we can't have a lot of tools at ready disposal except for the person on the arm, and of course your space limited there. So of all these tools, it sounds like an awful lot, over 200 different unique tools. We only have about approximately 50 that we nominally will use, and they're always at our disposal, all 200 of those. In this garage or in the payload bay where we're working, of course, at the aft end, as I'm sure you've heard in earlier briefings, is where the ST will be parked on the FSS, or Flight Support System structure. That will be at the very back of the payload bay, so it's approximately 30, 40 feet away from the airlock anytime that we're working back there. Now, if you're in your garage working on something and you need a tool that you don't have, nothing to walk 30 or 40 feet and go get your tool. But that's a lot of overhead for us in the payload bay to have to go to the airlock to get a tool. It's a 5 to 10 minute task just to translate there and back. So we try to have all the tools we're going to use on the day with us when we get out of the airlock. So we actually go through the choreography, setting up for any EVA day what tools we're going to need, have those either on the end of the arm or with us to save us that trip back to the airlock. Now, all these tools, as I mentioned, procedures that we ended up with, we ended up inheriting those when we were assigned to crew, and a lot of people did a lot of hard work getting it. And the tools that we have, we're really indebted to the tool folks here at SC and up at Goddard for not only giving us the tools that are EVA friendly, but actually modifying some existing tools as we went through training to make our task not only easier but more efficient, so that we can save EVA time up there, and I'm sure the success that we're going to have is going to be a great part due to their efforts of making us the tools that we needed to be able to do the job. I think Jeff and Kate now are going to tell you a bit more in detail about the tasks they're going to be doing out in the payload bay.
I'd like to take off a little bit on Tom's analogy of the garage and how you use your tools before getting into the specifics of the task, because it's something that I like to tell people to explain our basic philosophy, that anybody who's ever done a car understands. You know, the number one rule when you go work on your car is don't hurt yourself. Number two, for God's sake, don't break anything that isn't already broken. And then only after you get past the first two things, then you worry about fixing the problems that exist. And that's exactly the philosophy that we have to follow here. We work with safety of the crew in the shuttle as our primary responsibility. We have to exercise exquisite care because we're going to be working in an environment with a lot of delicate hardware, and we certainly don't want to mess up anything that isn't broken now. Get on to the actual repairs. Say a little bit maybe about some of the EVA-friendly repairs specifically designed for change, and then maybe let Kathy say something about the more difficult things. The two things I think that are maybe closer to my heart than anything else as an old astronomer are the optical repairs that we'll be doing, and that's the WIFPIC, Wide Field Planetary Camera, and COSTAR. Now, these are the largest pieces of equipment that will be moving around, and it's when we move around these huge pieces of equipment we really appreciate Claude being able to drive us on the arm. As he said, we do have ways of getting these big pieces of equipment from one to the other without the arm, but it's a lot more difficult and a lot slower. We have practiced moving these things around underwater. Of course, there's difficulties getting a big simulation of water because you have the viscosity of the water, which causes it to be more difficult to get large objects moving. And makes it, of course, easier to get stopped, which is not true in space. All of us who are going to be doing the spacewalks have prior EVA experience, so I think we're in a good position to be able to appreciate the differences between the kinds of training that we've had and the actual space environment. But this will be a real test of putting in the WIFPIC COSTAR of whether you really can design large pieces of equipment for on-orbit repair and refurbishment, because this, of course, was the whole idea behind the Hubble telescope originally. The reason we were able to commit to building a project worth in excess of $1 billion is that it's the space shuttle that gives us the ability to maintain this sort of facility as a national observatory. This was what we signed up for a long time ago when the telescope was built, and this is what we now have to go demonstrate. And the WIFPIC and the COSTAR and some of the other equipment like the gyroscopes and the electronic control units really very nicely designed. There's a minimum of bolts to undo and do up. There's tracks that you slide the equipment in. It's amazing that we have to be able to position this optical equipment to an accuracy of better than a millimeter, and something that normally you'd have trouble doing even on the ground in your bare hands. And yet the system of tracks which guide the large pieces of equipment in place, and then a system of ladders which we can actuate will provide us with this sort of accuracy. Of course, we wish that everything on the telescope was so easy to work. Some things we're going to have to work a little bit harder on, and Kathy's going to talk about that.
I'll tell you specifically what we intend to do on each day. As Stuart said, we're prepared to adjust our plan to change our jobs each day, but we're very happy to stick with what we've been trying to do for a while. On the first day, there's a little bit of housekeeping to be done out there. The tools have to be moved out and positioned. The MFR has to be installed in the end of the RMS so that Claude can move us around to do our job. Low-gain cover has to go on the bottom of the telescope to protect the low-gain antenna from us as we work out there. We have some translation aids that have to be deployed. When that housekeeping is done, then Jeff and Story will start on the first task, which is to replace 2 of the sensing units in the telescope. They'll also change out 2 of the electronic control boxes and a number of pieces on the telescope, which have been determined to not be built according to spec, so they need to be checked out before the scientific instruments. And it doesn't sound like a lot. That'll be one very full EVA day. When they come in, we will completely clean and refurbish their suits so that they would be available for the next day if necessary. However, we're going to try to alternate teams to keep us a little bit fresher than we'd be if we had to go back-to-back-to-back EVAs, although we are capable of that as well. Tom and I will go out on the second EVA day and place both solar arrays. The solar arrays are the first of the fairly massive objects that we're going to move around in zero gravity. Our training for that comes not so much from the water tank, but from air-bearing floor training that we have done in Building 9. That's the only chance we have to move these massive objects around in an almost frictionless environment. Water certainly doesn't qualify for almost frictionless. It takes a great deal of effort to push those objects around in the water tank. So that in itself is negative training. We try to get an idea of what it's really going to feel like to move those from the air-bearing floor. In the water tank, we get down our choreography of who does what and actually mating the interfaces and doing the bolts. And that is fairly realistic in water. However, moving objects is not. It'll take a whole day to replace both solar arrays. Take off the -V2 solar array first, and we have to put that in a temporary stowage bracket to get it out of our way. We'll remove the new -V2 array and install it on the telescope, remake all the electrical connections and the latches that hold it to the telescope. We'll stand back and hopefully get a chance to look at the stars or the Earth or whatever's in view at the time while the telescope is rotated 180 degrees, and then we'll proceed to do the +2 array in the same manner. With that, we have to stow the old array that's temporarily stowed on the side of the orbiter, and it may not sound like a full day, but that's a full EVA. On the third day, the first of the scientific instruments will go in the wide field planetary camera. Jeff and Story will remove the old one. Again, we have a temporary stowage position on the side of the orbiter to get out of our way while we install the new wide field planetary camera. That's a very delicate operation. It's not a difficult one, but very delicate in that the mirror sticks out front with no protection once you remove the mirror cover. This very delicate and expensive and very safe mirror is the first thing that goes in the cavity. So it's going to be very important to do that slowly, carefully, and very precisely to protect that. When complete, they're going to have time to do one more job that day, and that's to replace the magnetometers. Those are located near the top end of the telescope, which is a little bit out of reach of the mechanical arm. So we'll tilt the telescope down to them about 15 degrees and allow them to install new magnetometers on the top of the old ones, and it goes up. The EVA day, Tom and I go back out, and we will remove the HSP from the telescope, stow it on the same bracket the whiff pick had been temporarily stowed on, replace that with the star. That's the largest, most massive object that we're moving around. It also has one delicate corner where the dipole optical bench comes out. We're going to try very hard not to bump that. It's something about the size of a phone booth, and we're sticking it in a hole which is probably only an inch taller than the box we're sticking in. So that's something that will very slowly, and if you wonder on the ground what's taken so long, it's that we have to be careful. It's so important how fast we get the job done, but it is very, very important that we do it right and do it carefully. We'll also that day add a coprocessor computer that's running the telescope to add some additional memory to that. This day has a couple tasks on it. It's not scheduled as a full EVA day, but it'll give us margin in case some of the other tasks run longer than we think. The GHRS repair kit will install to add some redundancy to the high resolution spectrometer on board, and also the SADI electronics box for the solar will be replaced on that day. It's one of the tasks that was not planned to be done, and so it's a little bit more difficult than the very elegant tasks that were anticipated when the scope was built. There's some very small bolts to hold that box to the telescope, and they have to be removed and captured with a gloved hand, along with the washers that are on them instead of trash bags. We'll hope at all 6 of them. There's a chance might not, but we're going to give it our best shot. We'll replace that box. It also has little connectors on it, similar to what you have on your computer, with these little D connectors with tiny, tiny screws that have to be backed out and reinserted. And that in itself will take a long time. It'll look like we're standing out there not doing much, but it's also a time-consuming task, all those little tiny screws back where they came from. When that's complete, our EVA job is done. The solar arrays will be deployed today. and then we'll hand it over to Claude as a complete and refurbished telescope to be deployed.
Now, the deploy on day 9 does not consist only releasing the telescope and backing away from it, obviously. There's a lot of preparation work that has to be done on the telescope itself, on the orbiter, and on the arm in order to be ready for the release. We have to realize that after release, we won't be able to get back to the telescope several months or several years, planned 3 years, which is a time span between servicing mission of the Hubble Space Telescope. The configuration of the telescope will be performed by the Space Telescope Operation Control Center at Goddard Space Flight Center. We'll configure the orbiter and the arm fully before the release. As far as the telescope is concerned, obviously solar arrays will already be deployed. This should be done on the 5th EVA day, as Katie mentioned. The high-gain antenna will have deployed also, and the aperture door covering the top of the telescope will have to be commanded open also. The reason why this is done prior to release is that we want to be sure that this door can be opened by command from the ground before reaching the telescope. We don't want to release the telescope, realize after we separate it from us we can't open that door. There's always a capability, BVA means, to crank that door open in case the command doesn't work. The release itself is going to be done inside a certain window that relates to lighting condition, communication capabilities with the ground. And within that window, after the telescope will have been put in the proper position above the Gore Bay using the remote manipulator system, at some point I will release the snare, back away the arm, put the brakes on, and then Sox will go over to do the separation. Separation in 3 steps we can talk about, as well as about the last through the mission and the re-entry and landing.
Well, there's a few sequences we may actually end up doing to get away from the telescope, but they all have some things in common. One of those is a very small burn to get us moving initially away from the telescope, and then another 1 or 2 burns a short time later to bring us to a lower orbit and get us separating and setting us up for the orbit burn. I'm sure there'll be some mixed emotions on board when we're backing away from the telescope. There'll be some jubilation, I think, for the task that we've been able to accomplish. And I imagine there'll be a little bit of sadness, too, because our time on orbit will coming to an end, and the back-away telescope will mark that very, very brightly. Over the 2 days, we'll have a lot of work to do, packing up the orbiter, getting everything ready to come home. Whenever you come back from a vacation, you know what it's like to repack your suitcase. Well, it's even harder on the orbiter. There's lots of nooks and crannies that we have to find and put all the things back in. That'll keep everybody's minds busy. The actual end of the flight will occur about flight day 12. We'll do the orbit burn. It'll be 300, 400 miles per hour that will slow down the orbiter's velocity. That cause our orbit to down into the Earth's atmosphere, and the atmosphere will cause the vehicle and slow us down to the final landing velocity. We'll be landing at night, either at KSC or Edwards. I hope, unlike for me, I get to land where my family is. But you can never predict that, and we don't know what the weather's going to be 12 days after we get off. Covey will do a super job landing. I'm sure we've been getting lots of practice in the STA and at night. I don't think I've flown as much at night here, and maybe when I was out in the Navy, we flew a lot at night there out on the carrier. But this is probably a personal record for me in about the last 5 years, the number of night hours we're getting. I guess I'll turn it over to Covey now to wrap things up and summarize what we'll be doing.
Okay, well, thanks. This has been a brief time, crew, to talk to you about the activities that we expect to participate in. I want to close the comments with some thoughts. 8 years ago, I sat at a similar conference as we prepared for a mission that had many of the same type of elements that this is EVA, a satellite repair, and lots of RMS operations. And the commander was Joe, and at that time, he described the level of crew activity by saying that we were as busy as we were puppies. I think that probably is true for us right now, too. We have been incredibly busy, particularly over the last 2 weeks. But our level of activity now is starting to settle down. We're able to reflect directly on those tasks ahead of us and how we have prepared for them. To give you a perspective of that, Story and Jeff made their last new buoyancy run yesterday. Kathy and Tom will make their last run tomorrow. So that's the end of the neutral buoyancy runs for them. If you think in terms of the fact that they've spent collectively over 400 hours in neutral buoyancy and training, at the end of a very big activity. We've completed almost all of our shuttle simulation training, except for some ascent and entry integrated simulations that will occur tomorrow and early next week. And then we will go into a quarantine and begin shifting to basically about 12 hours on Wednesday of next week. We'll spend Thanksgiving in quarantine, but it probably won't be so bad because we'll be sleeping between 11 and 7 o'clock, 11 in the morning at 7 p.m. Thanksgiving Day. And we will continue that sleep pattern up until the time we fly. In summary, the crew is really ready. This crew has more space shuttle experience than any other space shuttle flight. We have 16 flights collectively between us. As soon as we get into orbit, that's going to be 23. If you think in terms of those terms, it's incredible. But that has helped us to get through the training that we have, get to the point where we are. More important than the crew being ready, the team is ready. That's the spatial program, the Hubble project, the mission operations team. They're all ready. They're ready. They have prepared themselves more for this mission than I've seen for any other space flight. The intensity of our integrated simulations is far beyond what I think that I personally have ever seen, and that would include STS-61, where we did a lot of integrated training. That makes me feel very good. I know that when we're in flight, safely in orbit, that we're going to have the support of a superior and superb team. And if we're going to do this mission right and get it done, all of the objectives done the way we can, it's going to take the whole team, not just us in orbit. That, Kyle, I'll turn it back to you.
Okay, great. We're ready for questions, and I would like to ask everybody along that's going to ask questions is to identify the crew member. That'll help audio folks a great deal. We'll start here at JSC, and then we'll go to KSC and Goddard as we did in the last briefing. We'll start with Mark.
This is Mark Carruth, Houston Chronicle, and I guess for story, but maybe others could add to this, but could you sort of explain how the EVA team was paired up, realizing there's flexibility and you can match as you need to, but and when this was gelled or firmed up?
The time I'd say was roughly about a year ago. I just polled people and talked to people and kind of got their preferences. No one had any really strong preferences, so kind of sort of fell out like that. And KT had obviously they'd worked together on STS-49, so they were a team already. They had struck their wrist already there, but that didn't necessarily dictate the way it was here. We just really got together and just kind of talked, but it turns out there were no really strong drivers. You could have just thrown us up like dice and let it all back down, and that would have worked very well too.
Any more questions here? Start right here, Steve.
Steve Gilvain, KTRK-TV. I'd like to ask a question I had in the earlier briefing, and that's fatigue. Story perhaps you want to start with. How do you guard against fatigue after all of the hours been put in so far?
Are you starting with me for any particular reason? Well, it probably starts on round. We had an awful lot of integrated simulation for 50 hours in the simulators. Last week, Monday, we were integrating another simulation Tuesday, and we spent 8 hours in the water tank yesterday. So getting ready for the Olympics, we're peaked out right here. Now we'll start, Kate and Tom got their 8-hour run on Friday. But we'll start slacking off and resting up just a little bit, going back to 10-hour days now. And I think that'll come out exactly right for the flight. But Steve, we do have to look at fatigue. We've got to be reflective enough to let ourselves ensure we're rested. We do have a day off that is scheduled in there, so in case we run into any tasks which need to be researched, we run into some prize and need some research on the ground, we can take a day off for that reason. Or if the rest of the team sees that we've been pushing pretty hard and put the day off, then regroup and pick up from there. But I think the training we've had on the ground has gotten us up, in really pretty fit shape to be able to perform well with the amount of jobs that we need to do. The person inside, too, you think about the people inside, too. I find I'm just as tired with all the real concentration and focus conducting the symphonies inside as outside. So I'd say it's basically the kind of training and preparation we've had. It's a reflectivity to be sure that we look at ourselves, what state of fatigue is, and taking a day off and taking a break if we need one.
I'd like to comment on that. Just to give you an example of the best simulation we probably had of what it's like to do all these repetitive EVA days was in October when the crew went to the Hubble Space Flight Center for 2 weeks to do neutral buoyancy runs there. We had most of the crew there for most of the days, but the EVA crew members at that time, we did every day we were doing 6-7 hour runs in neutral buoyancy, and some days was back-to-back the same team. So Story and Jeff would one day, and the very next day they would go in again. So we got a chance to see what it was like in that environment with long neutral buoyancy runs for the same crew members to go back and to get a feel for that. To show you how that went, they'd get out and we'd go back and get something to eat, and they'd say, well, when do we go to the gym? Fatigue was not an issue to the point where we were concerned about it in the runs. That's the kind of openness that I've used to consider what I might expect on orbit. But I feel that I ultimately on board have to be one that will make the call on whether or not I perceive the VA crew members or the other crew members as being fatigued to the point where we need to take our day off. And it's built that way, the flight plan is built so we can do that when we need it.
Just a one for Claude, please. You're still using the virtual reality, and that will actually work out in overall
We
things.
have used it more as an evaluation tool for positioning of the EVA crew member to tip of the arm for various tasks, and also the kinematics of the arm motion from one thing to the other, whether we got to reach limits or singularities in the geometry. We did not use it extensively for training, to more as an evaluation tool before the runs in the water. But this has been a very good tool.
It's been 6 months probably we've really done any virtual reality work, and it was mainly development work that we used it for.
Peter Ann with Newsweek, mainly for the EVA team, but everywhere else, what's been the most memorable or pivotal part of your training?
One or two burns a short time later to bring us to a lower orbit and get it separating and setting us for the final deorbit burn. I'm sure there'll be some mixed emotions on board when we're backing away from the telescope. There'll be some jubilation, I think, for the task that we've been able to accomplish. And I imagine there'll be a little bit of sadness, too, because our time on orbit will be coming to an end, and the back away from the telescope will mark that very, very brightly. Over the next 2 days, we'll have a lot of work to do, picking up the orbiter, getting everything to come home. Whenever you come back from a vacation, you know what it's like to repack your suitcase. Well, it's even harder on the orbiter. There's lots of nooks and crannies that we have to find and put all the things back into. That'll keep everybody's minds busy. The actual end of the flight will occur about flight day 12. We'll do the deorbit burn. It'll be 300, 400 miles per hour that will slow down the orbiter's velocity. That'll cause our orbit to dip down into the Earth's atmosphere, and the atmosphere will cause drag in the vehicle and slow us down to final landing velocity. We'll be landing at night, either at Covey or Edwards. I hope on this flight for me, I get to land where my family is. But you can predict that, and we don't know what the weather's going to be 12 days after we take off. Covey will do a super job on the landing. I'm sure we've been getting lots of practice in the STA, flying at night. I don't think I've flown as much at night here, except maybe when I was out in the Navy. We flew a lot at night there out on the carrier. But this is probably a personal record for me in about the last 5 years, the number of night hours I've been getting. I guess I'll turn it over to Covey now to talk about, to wrap things up and summarize what we'll be doing.
Okay, well thanks. This has been a brief time for the crew to talk to you about the activities that expect to participate in. I want to close the comments here with just some thoughts. 8 years ago, I sat at a similar press conference as we prepared for a mission that had many of the same type of elements that this does, EVA, satellite repair, and RMS operations. And the commander was Joe Engle, and at that time, he described the level of crew activity by saying we were as busy as a litter of puppies. I think that probably is true for us right now, too. We have been incredibly busy, particularly over the last 2 weeks. But our level of activity now is to settle down where we're able to reflect directly on those tasks ahead of us, and we have prepared for them. To give you a perspective of that, Free and Jeff made their last neutral buoyancy run yesterday. Kathy and Tom will make last run tomorrow. So that's the end of the neutral buoyancy runs for them. If you think in terms of the fact that they've spent collectively over 400 hours in neutral buoyancy training, that's a very big activity. We've completed almost all of our shuttle simulation training except for some ascent and entry integrated simulations that will occur tomorrow and early next week. And then we will go into quarantine and begin shifting to basically about 12 hours on Wednesday of next week. So we'll spend Thanksgiving in quarantine, but it probably won't be so bad because we'll be sleeping between 11 and 7 o'clock, 11 in the morning at 7 p.m. On Thanksgiving Day. And we'll continue that sleep pattern up until the time we fly. In summary, the crew is really ready. This crew has more space shuttle experience than any other space shuttle flight. We have 16 flights collectively between us. As soon as we get into orbit, that's going to be 23. If you think in terms of those terms, it's incredible. But that has helped us to get through the training that we have and to get to the point where we are. More important than the crew being ready, the team is ready. That's the Space Shuttle program, the Hubble project, the mission operations team. They're all ready. They're very ready. They have prepared themselves more for this mission than I've seen for any other space flight. The intensity of our integrated simulations are beyond what I think that I personally have ever seen, and that would include STS-20, where we did a lot of integrated training. That makes me feel very good. I know that when we're in flight, safely in orbit, that we're going to have the support of a superior and superb grounding. And if we're going to do this mission right, get it done, all of the objectives done the way we planned, it's going to take total team, not just an orbit. With that, I'll turn it back to you.
Okay, great. We're ready for questions, and I'd like to ask everybody along the net that's going to ask questions to identify the crew member, and it'll help our audio folks a great deal this morning. We'll start here at JS, and then we'll go to KSC and Goddard as we did in the last briefing. We'll start with Mark.
This is Mark Carrubb, Houston Chronicle. And I guess for story, but maybe others could add this, but could you sort of explain how the EVA team was paired up, realizing flexibility and you can mix and match as you need to, and when this was gelled or firmed up?
The time I'd say was roughly about a year ago. I just polled people and talked to people and kind of got their preference. No one had any really strong preferences, so kind of sorted out and fell out like this. Tom and KT had obviously they'd worked together on STS-61, so they were a team already. They had struck their already there, but that didn't necessarily dictate the way it would be here. So we really got together and just kind of talked. But it turns out there were no really strong groups. You could have thrown us up like dice, let us fall back down, and that would have worked very well too.
Any more questions here? Start right here with Steve.
Steve Gilvain, KTRK-TV. I'd like to ask a question I asked in the earlier briefing, and that's fatigue. Story, perhaps you want to start with this. How do you guard against fatigue after all of the hours that's been put in so far?
Are you starting with me for any particular reason? Well, it probably starts on the ground. We've had an awful lot of integrated simulators, go over 50 hours in the simulators. Last week, Monday, we were integrated. We had another simulation Tuesday, and we spent hours in the water tank yesterday. So, like getting ready for the Olympics, we're peaked out here. Now we'll start, KT and Tom got their 8-hour run on Friday. But we'll start slack off and resting up just a little bit and back to 8 or 10-hour days. Now, I think that'll come out exactly right for the flight. But see, we do have to look at fatigue. Got to be reflective enough to look at ourselves to be sure we do have a day off that is scheduled in there. So in case we run into any tasks which need to be researched, we run some prizes that need some research on the ground, we can take a day off for that reason. Or if the rest of the team sees that we've been pushing pretty hard, we can put the day off then, regroup, and pick it from there. But the training we've had on the ground has gotten us up, in really pretty good shape to be able to perform well with the amount of jobs that we need to. The person inside, too, you've got to think about the people inside, too. I find I'm just with all the real concentration and focus conducting this meet from inside as outside. So I'd say it's basically the kind of training and preparation we've had is a reflectivity to be sure that we look at ourselves, what our fatigue is, and taking a day off and taking a break. We need one.
I'd like to comment on that. Just to give an example of the best simulation we probably had of what it's like to do a lot of these repetitive VA days was in October when crew went to the Mars Space Flight Center for 2 weeks to do neutral buoyancy runs there. We had the crew there for most of the days, but the EVA crew members at that time, we did every day, we're doing 7-hour runs in neutral buoyancy, and some days it was back-to-back the same team. So Story and Jay would go in one day, and the very next day they would win again. So we got a chance to see what it was like in that environment with long neutral buoyancy runs for the same crew members to go back-to-back and to get a feel for that. To show you how that went, they get out, and these guys would get out, and we'd go back and get something to eat, and they'd say, well, when do we go to the gym? Fatigue, not an issue to the point where we were concerned about it in those runs. That's kind of a litmus that I've used to consider what I might expect on orbit. But I feel that I ultimately on board have to be the one that will make the call on whether or not I perceive the EVA crew members or the other crew members as being fatigued to the point where we need to take our day off. And it's built that way, the flight plan's that way, so we can do that when needed.
Just a quick one for Claude, please. You still using the virtual reality, and how did that actually work out in your role?
We have used it more as an evaluation tool for positioning of the EVA crew member, the tip of the arm for various tasks, and also the kinematics of the arm motion from one position to the other, whether we need to reach limits or singularity in the arm geometry. We did not use it extensively for training, to more as an evaluation tool before we did the runs in the water. But this is a very useful tool.
It's been 6 months probably since we really did any virtual reality work, and it was mostly development work that we used for.
Peter N. with Newek, mainly for the EVA, but everybody else, what's been the most memorable or pivotal part of your training?
Everybody's waiting to see who's going to take that because nobody wants to.
Let me start. I mean, I think in terms of pivotal, I'd have to say when the last trip that we made to the neutral buoyancy tank at Marshall sort of looked at as our big dress rehearsal, and that was a big test. And I think when we finished those 2 weeks and had gone through all the tasks that we're planning to do in the flight, and everything had really gone well, and like Dick said, we had actually ended up doing some back-to EVAs. I think that's really just the feeling that at that time we were ready. Sure, we had more simulations to do back in Houston and some more, another month before flight. But at that time, I think we all felt that we were confident that we were going to be there, that we had learned how to do, and that we were ready to.
There's other significant milestones. We went to the Clinton Goddard Space Flight Center. We had all the hardware, the WIFPIC, the CoStar, co-processor, magnetizers, everything else And it was sort of like a playroom that you go in and work with the actual hardware you're going to work with. It's very, very important because the mock-ups in the water do not reflect the actual hardware. Our familiarity with the things we're going to have to deal with, learning all the mechanism latches and our interfaces, that's a very, very significant part of our training. When you talk about, as Jeff says, pivotal point, when we finally got done the last run there, we looked around at our room and it was empty. There was nothing left there, so we said, wow, that job is done. And then going down we'll go on Sunday for interface verification testing with all the hardware that I mentioned out in the bay, the ORU carriers, solar array carriers, the flight support structure and that thing. They will be mounted in the orbiter, and we will operate them from the flight deck in the orbiter this Sunday. So going down the flight and seeing all the hardware arrive down, that's a kind of another pivotal point. When we leave interface verification test this Sunday, then we will know the job is really done and it's time to go fly. There are milestones like that.
Okay, we're going to go to the other center now. We'll start by going to the Kennedy Space Center in Florida.
Yeah, hi, Bill Howard with CBS. I have several questions. For training, and I can answer this, I was curious if anybody had a ballpark idea of the total hours you spent training and the total hours of wet work for the EVA folks. And the third part of that is, what's normal for an EVA mission? If somebody can put some numbers on that.
Can you compare it to what y'all did for 49?
I think on 49 that it was something over 200 hours compared to 400 hours of weather concepts, a factor of twice as many for this flight as STS-49. Of course, that's not comparing apples and apples because on STS-49 we basically had two tasks. We had the INFOSAT EVA and then we had the ASIM task, where on this mission we actually have 5 different EVA days of tasks to do. So it's obviously, the bottom line is in a year's training, we ended up with significantly more time in the water on this mission, both than we did on STS-49. And I really don't answer to how much total training time that we put in. It seems like the last couple of months that what we've been doing 12 hours a day. I guess one of the pivotal points, I think, for me on the training is going to be when we launch and it's over. We're going to go do it.
I could comment on the overall training load. To put it in perspective, of a normal space flight, we try to name the crew 12 months before flight. They begin their training 9 months before flight, with intensity beginning at 6 months before flight. This crew, the first crew member was named over a year and a half ago, and that was Story. The other EVA crew members were named a year ago in August. And basically, from that time they were assigned, this has been the total focus of their activity, is preparing for this mission. Now, all training, there's a lot of other aspects of preparing for the mission. The remainder was named in December, and we started formal training 1 month later in January, and that was earlier than normal. That had to do with the fact that there was additional load because of the training required for RMS operation, rendezvous, and in my mind also starting early was going to be able to accommodate things that were not part of a formal training plan but evolved. And specifically, the Marshall Space Flight Center's neutral buoyancy simulator made upgrades to their remote manipulator system, and those upgrades were in place for the October runs that were done. That allowed Claude and SOC to spend entire EV runs over there operating the RMS in the most realistic environment that we have for training RMS EVA integrated operations. That wasn't part of their training plan. That was something that we were able to accommodate and to achieve invaluable training because of we started the rest of the training. Probably the one area that you could pinpoint has more training than other flight is the integrated simulation, the joint integrated simulation area. We simulated almost every day for this mission, and in some form or fashion, except for our day off. It's the only one that we didn't simulate. And many of those days we simulated them once. That is extraordinary when you consider the fact that the mission is 11 days long.
Thank you. And for Story, what is, a dumb question here, what is the contingency if the FSS fails to rotate or fails to tilt? I mean, can you guys go crank it around or do whatever you have to manually?
Yes, we can, Bill. Those are basically very simple tasks to undo. We can undo the launch lock that holds the table down. We can pivot it up, and we have a what's called a post that we can install to keep it in one of two positions, and we also rotate it manually. Those tasks are quite simple. In general, it's put a power tool on a 7/16" bolt. One of them releases the mechanism, the other turns it. They're throughout the flight support structure, the carriers and the telescope. There are backup contingency ways of getting their normal functions done.
Thanks. I have just one more question, but it's got two parts. One for Jeff Hoffman and one for Commander. Jeff, you've done this many times, but if you do it one more time, I'm trying to get a feel for how folks view the importance of fixing Hubble to astronomy, to American astronomy, to big science in the United States. And for Commander Covey, I was looking for a similar kind of philosophical look at the importance of this mission NASA to Hubble and showing you can demonstrate on-orbit servicing.
Astronomy is entered a new era in the space age, and the Hubble Telescope is really the culmination of this. It's of course one of NASA's great observatories. It's the premier observatory of the last part of this century and the first part of the next century. Despite the incredible advances in ground-based astronomy, there are things that nothing else will be able to do better than the Hubble Space Telescope until we have observatories on the moon. And so it's incredibly important for the future of the astronomical community. So much can come out of a repaired Hubble telescope. So much has gone into the project. And of course, the astronomical importance, I think one of the very gratifying things for astronomers is the incredible public interest in the Hubble telescope, which is extraordinary when you consider this is a pure scientific endeavor, and yet from the beginning, so the Hubble telescope has caught public's imagination. I think because some of the astronomical questions which the Hubble telescope is able to solve, like the origins of the universe as we know it, the search for other planetary systems, the discovery of black holes in other galaxies, so many things which somehow at a very deep level excite those imagination. We're just on the verge of being able to answer some of these questions, and hopefully after we get the Hubble back into perfect working order, we'll be able to answer them. So it's not just for astronomy, I think it's for our entire culture, our entire civilization is invested in this.
On the second part of your question, Bill, we've been told this mission is very important to NASA. It comes from that, and being told that from a variety of sources. And I feel that it is an important mission, but every space shuttle flight we fly is important for one reason or another. This mission, though, probably has some singular importance in the fact that the Hubble Space Telescope, when deployed and had the spherical aberration, that was an embarrassment to the agency. And the agency has found a way to work its way back out of that embarrassment. The other side of that is that the Hubble Space Telescope is performing incredibly well and returning magnificent science and making discoveries even with its spherical aberration. The fact that the telescope was designed to be serviced, repaired in orbit probably lends to the real importance of this mission from the standpoint, can NASA design a spacecraft? Can we design and operate a spacecraft that can be in orbit for a period of time and be serviced? You could take that as a parallel to space station operations. Can you maintain service space station? We may be a forerunner of some of the techniques and the ideas of servicing may be required for the space station. All of us on the crew recognize that success on this mission is very important to NASA and to our science community. We feel that because of the importance of it, there is some additional pressure to perform, but The real performance issue for the crew is self-motivation and self-driven. It comes from the fact that we've been able to do a job that we want to go do, and we're going to do our very best job no matter what. And we play down the importance to the agency, and the fact that the importance is just to do our job the best we can.
This is Pat Huggins, WMSU Radio. Along those same lines, and I guess Story Musgrave or Jeff Hoffman addressed this, there's a small but reasonably vocal group of scientists, I guess you could call them the bird hand is worth two in the bush crowd, who seem to think that on Hubble they're good science now, and if a group of astronauts, no matter how well trained and how intentioned, start working with that optics, liable to damage something, and then they'd be worse shape than they were when Hubble went up. Reasonably speaking, how much reassurance can you give them that when all is said and done, Hubble won't be any worse off than it is now?
Let me go back to the I made at the beginning. In order of importance, before fixing anything, make sure that we don't do something that isn't already broken. And we are constantly going to be looking over each other's shoulders. You're going to hear us talking, narrating every step that we're taking, so that in case we may forget something, somebody inside will catch it, somebody on the ground will catch it. We're going to be documenting everything we're doing. We're going to be moving slowly. We have had extensive discussions with the people who know the hardware best about where the most delicate operations are, what delicate pieces of hardware which we have to be especially careful of. Quality control is to be foremost in our minds. And we're not going to forget that. There's no question. Anytime we go near to a complex piece of machinery like this, we are taking calculated risks. And, we accept that. The Shuttle project accepts it. The Hubble Telescope project accepts it. And to put it in perspective, I should say, it is true the Hubble Telescope, as it presently exists, is doing first-class science and could continue to carry on doing first-class science. But unless we make these repairs, it will not fulfill the dream of the people who spent so much time developing this equipment. In its present condition, it can't take us out to the edge of the universe. It can't take us back to the beginning of time. It's not going to get us to the point where we can get a real estimate of perhaps the number of stars in our galaxy with other planetary systems. These philosophical questions, which are so important to humanity, are not going to be solved unless we go and fix it. And so I think the very tiny risks, which we are doing our best to minimize, that we're not going to hurt anything, is worth taking because the reward is so great.
The improvement of science is the one thing, but storing a redundancy, guaranteeing the health of Hubble for another 4, 5, 10, or even 20 years. The solar arrays, due to thermal deformation, they introduce a jitter. This is corrected somewhat by changes in the software, but that requires an awful lot of memory to run the software program, and also the structural deformations. You wonder about structural fatigue. Eventually, replacing solar arrays is important to the health of the telescope. We've lost 3 out of the 6 rate gyros, which are very important, actually essential for the health of the telescope and scientific pointing. We've lost 3 out of 6. It's very important. If we lose one more, we're down to a no-science mode. It's very important to restore redundancy. We are now limited somewhat by the places in the sky we can point the telescope due to cost of solar array drive electronics. We're going to replace that and the capability to point the telescope anywhere in the sky. We want to add redundancy, the GHRS, redundancy to that system there too. The computer has lost roughly about 50% of its memory. When you add the coprocessor, we'll be back to 100% of the memory. So not only are we trying to correct the aberration in the science up to the original specifications, but I think in terms of redundancy in the basic health telescope for another decade or more, it's very important in what we're doing.
This is Sue Butler. I'd like to follow up some question just asked. How worried are each of you spacewalkers, let's have an answer from each of you, that you might accidentally do something that aggravates the problem? And are you going to be worried while you're working what impact the wrong move may have on what impact it would have on NASA's reputation? Are thoughts going to enter your mind while you are looking at it and consequences?
I think that's going to be foremost on our mind all the time we're working out there. Every time we move, that we're not going to be touching something or bumping something that could damage anything. That's something in all of our training, in our wetter front, we consciously watch each other and point out in time that one of us is even getting close to something to warn them ahead of time. So it's going to be foremost on our mind, something we're always thinking about.
Remember what Kathy said earlier about how slowly we're going to be moving, and you're going to be watching some of the EVA on television and wondering, what are they doing? You know, why aren't they moving? You know, one reason we are moving so slow is because we want to think through every move. But as far as what will be going through my mind, my experience on critical operations on previous flights is that the focus on the job is complete. I don't expect to have going through my mind what all the people around are thinking, what impact this has on NASA, on the astronautical community. I expect to be 100% focused on getting the job done and getting it done safely and correctly.
This is Marcia Dunn with the Associated Press for Claude. How much harder does your job become if the RMS develop problems, if a joint goes out, if you have to operate it manually? And how capture Hubble if you don't have a robot arm to use?
Okay, for the first question, we trained extensively degraded modes of operation of the arm. Single-mode operation, or if we have a failure of the slow mode of operation of the arm, we can use the rougher, coarse modes of the arm. So we have trained extensively so that if we have an arm that we have to operate with computer support in single mode, I'm confident that we'll do as well the capture of the telescope, the support of the ears, and the release of the telescope. Now, if the arm is completely, if prior to we have an arm that is completely sick so that we can't use it in order to grab telescope, there are techniques that have been developed in order to do a slow approach to the telescope. The telescope would be approached so that it would arrive in the back of the cargo bay, and EVA crew members would grab it and install it on a service structure, and then the hatches will be commanded in the closed position. So we have ways of capturing the telescope with the remote manipulator system, although it will be much more difficult task than in the way we planned it.
I guess I'd like to comment on the last part Claude talked about. Sox and I have looked in some of our simulators at what it would take to fly to the telescope and using aids that exist on the telescope itself and on the flight support structure in a docking type approach. But that's only been a look by us, and we really at this point have no plan to do that. The program has not bought into any plan of trying that type of an approach to the telescope. If the RMS, I mean, it's a really big day if the RMS, when we get into orbit and it doesn't have any of its mode at all. And I suspect that if we're there and that happens, that we'll probably stop and everybody will talk about it. We'll know some of the ideas that we thought about that might be looked at in that case to help us do that. Right now, there's no plan to do an RMS type capture of the telescope.
Would such a capture require two or spacewalkers?
We haven't looked at it at all. And our idea was that you could probably do it too if you could. The biggest problem is getting the telescope to the right place, flying it, and whether you would use EVA crew members to assist and how you would do that. We'd have to look at more.
Dave Shaver, I'm for service in England. Question Story and then a follow-up Claude. Story, what work has been done on looking at the wear and tear on the EVA? Because I think a lot of the work is hands-on. Are you taking spare gloves, or how are you looking at it?
I'd say probably the work that we've done in the water tank, we have a single set of training gloves in which we do 6-hour runs month after month after month. So looking at when we started developing what we call the EMU shuttle program, we added a database that says how much use do these gloves get. But basically, training gloves which see hundreds of hours, they are kind of the lead-in. They're the test kind of thing that you can look for wear and tear on. Our flight gloves, the ones we're flying on, high-time gloves, like my high-time gloves, only have a total of, my flight gloves have 30 hours on them. My back pair of gloves only have 25 hours, and that time is in a very clean, protected vac chamber. My training gloves have hundreds and hundreds of hours on them, so I said they don't get that much severe wear. Hubble, for the most part, is incredibly friendly. It does not take a lot of intensive work. Most of the work is done with power tools.
For Claude, your role in S2 and primary RMS base is a master European crew member. I want you to comment on your view of the future European crew members, the Russians coming up and Europeans and Canadians trained as mission specialists in Group 10.
Okay. Well, I must say I'm very privileged to have been elected for this team as a MS2 and as an RMS operator. In fact, there was no obligation by NASA on the basis of agreement with the European Space Agency to have ESA crew member on board any of the deploy or servicing missions of the Hubble Space Telescope. So I really feel privileged. I think that the whole project has been a great example in the international cooperation. Of course, there have been other examples, the Space Lab program and this one now, and of course there are the future cooperation programs, Canada and Japan and Russia for the space station. But I think things have been going very smoothly in the technical area and cooperation area, and all as far as the sharing of crew members for the servicing mission. For the future, of course, hopefully there will be more cooperative ventures of this nature, that is relatively small-scale cooperative ventures like the one we have on the Hubble Space Telescope, where the Europeans contribute 15% of the telescope and contributed one scientific instrument and solar arrays, and have 15% of the clock time for European astronomers. And beyond that, obviously, we'll have the space station. Of course, the program has been used completely, and I'm sure that we'll have mixed crews of various countries on board space station at the end of this decade and early next century, and I'm looking forward to it.
Fishery Shuttle with your Sentinel for Story Musgrave. If you could explain a little bit about useful work and sort of your concept, or did you steal that from somebody else, and how it's going to work out there?
Well, you'd have to ask my buddies here whether it's my idea or not. Useful work is to keep people working out there to choreograph so that you have two people working all the time. If you look at the total test that we want to do on the telescope, that adds up to a certain amount of work, a certain amount of time out there. And so you don't like to have someone that is sitting around not working because you're starting to fall behind. So useful work basically means looking at the total number of tasks, the total of bolts that need to be turned or connectors made or doors opened and closed and that kind of thing. And to be sure, to the best of our ability, to choreograph not only given tasks, there's two people working on that, to choreograph given days, the end of our days, and to be sure that we on board have the capability along with it, that when we get off the flight plan, and because of surprises, that we get a new kind of days that we can be as efficient as possible in terms of our allocation of tasks and keeping people working.
For Story and for Commander Covey, is there any concern on either of your parts, first for the payload in the sense of if for example, you have to leave in a hurry, you have to deorbit the next possible opportunity of having things in Hubble sort of configuration, say a door open, some bolts loosened for the next work, and overnight, I guess, some of the tools aren't going to be stowed. It's unlike previous flights where everything's put away after each EVA. I guess you're going to leave some things undone. What are your concerns on that?
Overnight, everything is safe. We put things over the tools on what all the MFR that are on the arms. They can be jettisoned and left out there. We do safe the bay for re-entry. Even as an absolute worst case, if we had a loss of cabin pressurization inside, we are trained to totally clean up the bay and make the orbiter safe in 20 minutes. That's the specifications we live to. And in our training, we've shown that we can do that in 12 minutes.
I guess my comment on that is that the overnight condition, we're probably in a much better configuration than we are during the actual EVAs. It would take more time for it to get things cleaned up and payload bay doors closed if an EVA was in progress and stories addressed, that we can do that in a specified time.
This is Janky of Florida today with a question for Commander Covey. There's been some talk around here about their last launch attempt might be before the Christmas holiday. And one of the issues that comes up about delaying the mission into January, should that be necessary, is that they don't want to give you 3 weeks off because of training. Would you be comfortable taking a couple of weeks off at the holidays and then being peak, ready to go first week of January?
We recognize that holidays, the Christmas holidays, are a potential impact to our training if we were to be delayed. So we've developed training plans now that will take us through the holidays, including training in the week during and after Christmas, and we would be as ready in January to fly as we'll be on the 1st of December.
And then sort of relate that, maybe if you don't get everything done on this mission and NASA decides to another one in late '94, will you guys be a prime crew for that?
Well, there have been various options that have been looked at as to what we'll do if we do have another mission to finish the work that's planned for this flight. Some of those options, if it was a quick turnaround, probably dictate that you would some of the same crew members, if not all. The longer the turnaround time, then you gain more options from the assignment standpoint as who or which of the crew members you would fly in, or if you would put additional crew members into the lineup. So it'd be the time frame between the two flights.
This is Bill from WESH-TV. Commander Covey, would you talk a bit about the rendezvous itself, the altitude and the amount of propellant that you have? If the rendezvous doesn't go the way it's supposed to go, how much extra propellant do you have to deal with that? At what point would you have to call things off?
Those are hard things to put a definitive number on. The rendezvous itself, this will be the highest rendezvous that we've flown the space shuttle. To get there with all of the payload that we are required to have to do the service mission means that we load all of our propellant tanks up as full as we can get them, both in our orbital maneuvering system, reaction control system. We're going with tanks full. We do not have a margin to accommodate a missed rendezvous for some reason. If we get close to the telescope and have to break it and re-rendezvous the following day, we will start eating into margins that mean a shorter mission, or we might not have the capability to do a re-rendezvous with any capability to do EVAs. Hubble is very high. It's be about 117 nautical miles when we rendezvous with it. We'll insert to an orbit that's probably on either 308 miles by a variable perigee, depending on how much phasing we have to do to the telescope. So we'll be going high. Going high costs lots of gas because you've got to save enough gas to come back down. And in order to protect all that, we do come with less we would really like to have is our capability to re-rendezvous, to try multiple attempts at a rendezvous. We definitely need to be successful on our first attempt.
Okay, that's it for Kennedy Space Center. We're going to go to the Goddard Flight Center now.
John Holloman, CNN, for Kathy and Tom. All of us on Earth watched you guys on the Intelsat mission. A question that I have is, how tired are you at the end of a long spacewalk? And physical exhaustion, is it mental exhaustion, or is it emotional exhaustion? What does it feel like in your body and your brain and your heart, I guess, as you're coming back in after one of these long spacewalks? Is there any concern that after doing 2 or 3 of these, you guys are going to be really peaked out?
I found that the fatigue that I experienced was more emotional and mental. You're focused completely on the next task you have to do and on getting the job done. I found it physically less taxing than the water tank. So if we can do back-to-back 6 or 7 hour EVAs in a water tank, then to do them in orbit should be less physically taxing. It's very fatiguing on the crew to be a part of an EVA. The guys inside can be just as tired as the guys outside. And And we'll gauge that as we go along and what need to put a day off in there. On STS-49, we did 2 EVA, took a day off while we regrouped and decided on what the options were grabbing Intelsat, and then with 2 more EVA, both of which were record lengths, the longest and the second longest EVAs that have been done. And at the end of those, I think we were tired, but we could done it again if we had needed to the next day. Tom did 2 of them.
And the good side of that for this mission compared to the task Kathy and I did on STS-61 with the ASIM, which was primarily all free-floating, very hand-intensive task. The tasks we're doing, as Stuart mentioned, are not that hand-intensive, and for the majority of the time, both crew members are in a foot race during the EVAs, which makes it much less fatiguing.
Earl Lane with Me for Story. Do you have any link concerns about how well your hands will hold up during these long EVs on the temperatures, or have the new gloves done the trick?
We've done all the testing, the result of my frostbite in the manned thermal vacuum testing. That was absolute worst case. The tool at minus 130, the tool at minus 300. It was a good test to run, but we have improved thermally an awful lot since then. We do not just keep the sun at the belly of the spaceship. We have multiple maneuvers that we do. We've improved thermally a lot in terms of attitude. We've done other things. We have more insulated gloves. We have a more insulated inner glove. We've taken the water flow off of the arms. We have additional layers of undergarments on the arms to keep the entire arms warm. And we have tested some of those concepts on STS-61, 57. We've gone back and Tom in the thermal vacuum chamber to test some of the fixes we've done. So it's something that we have to pay attention to. It's something we need to stay very sensitive to the temperature in our hands, but we have come a long way since the worst testing we did earlier. We're not anticipating anything.
We've heard twice this morning talk about opening the telescope at your door before you pull away with the shuttle. I'm wondering if there's any concern about contamination of the telescope from the hydrazine fuel that would be burned during that maneuver.
Yes, I can address that. In that the contamination issue was a concern. It was addressed throughout the development of the concept of opening the aperture door before we depart, and the risk of contamination was determined to be acceptable based upon the fact that it'd be nice to know that the door was going to be open. The risk of the door not opening after we left versus the contamination fell out in a direction that we don't think there's going to be any significant contamination by the separating with the door open.
Florida from the Baltimore Sun. It doesn't sound like there's much downtime into your days, but if there is some time, I'd like to know how the crew intends to spend it, to sort of relax from the pressure of either an EVA or just what's going on inside.
Well, I guess we have thought about how we're going to relax, because during the course of the EVAs, after they're done, all the work's going to be directed toward getting ready for the next one the next day. We may have a time to slow down. We're talking about the fact that Earth observations on this mission are not going to be something we're going to be able to do a lot of, but I suspect that for those few times when we are able to take a break from the preparations for the next day's activities, that people will do is take a look. 100-plus miles is a magnificent altitude to view the Earth from, and I'm sure we'll be taking advantage of that on the few times that we get to.
John Holloman, and one more time for the EVA folks. Bill Deflin said one of his worries, maybe his worry, was that on the day that you go out to roll up the solar panels, the old ones, they don't roll up. He said you got, or several people said you got several options of things you can do. What can you do if those pesky solar panels don't work again and try to retract them?
One of which is to retract them manually, put our tools on it and turn a 17-inch bolt and then manually. If they don't retract, then our plan is to put a grapple fixture on them, let them grab them and hold them overboard out of our way. We'll install the new solar arrays. When theirs are checked out, then we'll jettison the old ones. There's some things that are in between those two options that we have talked about, although I'm not sure the program is bought into, and that includes cutting the bi-stems, maybe throwing those away, but maintaining the blankets and rolling those in, and a number of things that we have talked about amongst the crew that are maybe possible, although not necessarily bought into by the program. But our basic plan is if they do not retract enough to stow them on the solar radiator, that we'll take them off either by hand or with the mechanical arm and overboard.
Okay, that's it from the other NASA centers, and we're back here. Any final wrap-up questions, Mark?
Mark Road, Houston Chronicle. I have a flight crew question. If there's proponent to reboost the telescope, could you kind of walk through what you would do, which jets would fire, and if there's any concern about adding contamination or forces on the telescope?
Yeah, the reboost is a pretty critical maneuver. We want to be very careful not to do the telescope, and there's been a lot of analysis done on which jets to use, exactly how to perform it. It basically goes if we tilt the telescope down, that orientation should help us with the loads. We'll be sticking out of the payload bay at about a 45-degree angle. If you were looking at it from outside, it ought to be pretty spectacular. We should do about 2 burns using the forward RCS. We hope that is where we'll have margin to do the burns, and they'd be separated by about 45 minutes or so as we burn it opposite side of the orbit to circularize the telescope in a nice orbit and minimize the decay that cuts in over the next few years.
Go ahead, Mark.
As a follow-up, too, do you have an electronic still camera on board as part of your equipment? Have you done any particular thinking or planning about using that if you needed to send images down to discuss any sort of planning or contingency? And how would you do that? Do you just shoot through the payload bay window? Can it go outside if you need to, or how would you be able to use that? Or is it really not much value?
By the time camera is not easily qualified, it'll stay in the cabin, and as we have used it on previous, it's invaluable if you want to get high resolution to the ground immediately. We're going to have it set up and plugged in the aft flight deck. Our plan calls for lots of electronic still camera pictures. At the end of the day, we will try to downlink the ones that we think are most interesting, the ones that involve information the ground may want to know before we deploy the telescope, how the areas looked when we closed them out, that sort of thing. If we have any kind of problem, certainly we will pictures and ship them to the ground immediately.
Okay. Do we have any questions here? Okay, I'll end announcing the things this afternoon. We're going to break, I guess, for lunch, and then we'll switch to Goddard, and we'll do some a mission overview briefing with the HST project folks from up there, and we'll also do a science brief, technical presentation from several folks also following that. Again, shortly after this briefing, we're going to replay the animation that Milt Heflin, who's the lead flight director, showed during his briefing earlier this morning. Thank you.